In the last video of this lecture, I want to talk about a result that's really useful at showing that polynomials are irreducible. This is usually referred to as Eisenstein's criterion, but Dummit and Foote point out that really it can be found in earlier work of Schoenemann. So they call it the Eisenstein-Schoenemann criterion, but from now on I'll probably forget and almost certainly refer to it as Eisenstein's criterion. So this is proposition 13 in section 9.4. And it sort of works on the same idea as the previous proposition, where we saw that a polynomial was irreducible by reducing all of the coefficients modulo some ideal I. Let's say that R is an integral domain and P is a prime ideal of R. Let's write f of x. This is a polynomial in R bracket x that's monic of degree n. So it's x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0. It's in R bracket x. So that means that all of these coefficients ai are in R. And we're going to suppose that an minus 1, an minus 2 down to a0 are all in this ideal P, but that a0 is not in the square of the ideal P, the product ideal P times P. And the conclusion is that f of x is irreducible in R bracket x. So before getting into the proof or anything, I just want to suggest that there's really only one way that this could go. You're working with some prime ideal P, and if you reduce all of the coefficients modulo P, then you're getting some. If this polynomial were reducible in R bracket x, you could use that factorization to get something about what happens when you look at the image of both sides of that equation in R mod P bracket x. So because we're working with this one prime ideal of R, this setup is really strongly suggesting that the thing to do is reduce all the coefficients modulo P and see what happens. All right, so before getting into the proof, I want to emphasize what this says for polynomials in Z bracket x, because that's certainly the situation in which I have most often seen this result applied. There, okay, so R would be Z. A prime ideal in Z is just PZ for some prime integer P. So let's say P is a prime integer. We have this polynomial x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0 in Z bracket x, where P divides an minus 1, an minus 2 down to a0, but P squared does not divide a0. So that's the translation of what it means for all the coefficients to be in the ideal, but a0 not to be in the square of the ideal. Then f of x is irreducible in Z bracket x, just like the conclusion here, and also in Q bracket x. So let me just say this follows from this proposition specialized to R equals Z, and corollary 6 of Gauss's lemma from last lecture told us that if you have a monic polynomial in Z bracket x, it's irreducible in Z bracket x if and only if it's irreducible in Q bracket x. The proof works how I suggested it would work. You suppose that f of x were reducible. And from what we said at the end of last lecture, that we also talked about when we were talking about the proof of proposition 12, f of x equals a of x times b of x for some non-constant monic polynomials, a of x and b of x in R bracket x. So now what we're going to do is we know something about the coefficients of f of x with respect to this ideal P. Let's reduce each coefficient modulo P on both sides. So what does that give? That gives a factorization in R mod P bracket x. On the left-hand side, every coefficient except the x to the n coefficient, which is 1, this monic leading term, every other coefficient is divisible or is in the ideal P. So when we reduce modulo P, all we get on the left-hand side is x to the n. On the right-hand side, what do we know about a of x and b of x? Not much, but we know that they're monic. So the reduction a of x bar and b of x bar, these are also monic polynomials of the same degrees as the degree of a of x and the degree of b of x. Okay, so an important observation is that since P is prime, R mod P is an integral domain. And the thing that makes this work is that, okay, we know that A of x and B of x are both not constant. And we claim that both the image of A of x and the image of B of x under this reduction have constant terms 0. And the idea is what would happen if the constant terms were not 0. So for example, if both of them had constant terms that were not 0, then you would get in the product of the image of A of x, the image of B of x, you would have the product of those two constant terms. And because we're in an integral domain, that would give a non-zero constant term on the right-hand side, which is not possible because the constant term on the left-hand side is 0. Okay, so one or the other of them has to be 0. Let's say that the constant term of the image of B of x is 0. So just take the lowest degree non-zero term of B of x. And then if A of x had a non-zero constant term, then you would get A of x, that constant term, times the lowest degree term over on B of x. And that would give a non-zero term over on the left-hand side. And there's just no way to cancel that out anywhere else. So that means that the constant term of A of x has to be 0 as well. Okay, so I'm going to pause and erase and show you how to use this observation to complete the proof. Let's finish the proof. So if the image of A of x has constant term 0 when we reduce all the coefficients mod p, and the image of B of x has constant term 0 when we reduce all the coefficients mod p, that means that the constant term of A of x is in P and the constant term of B of x is in P. But if A of x and B of x both had constant terms in this ideal P, then the constant term of f of x would have to be in P squared. And this is a contradiction. So what does that mean? That means that f of x was not actually reducible in R bracket x, so it's irreducible. All right, so the last thing I want to do in this lecture is give some applications of Eisenstein's criterion to show that certain polynomials are irreducible. It's pretty straightforward to come up with examples where you can apply Eisenstein's criterion directly. So what I want to do instead is highlight a trick that I really like, which is that f of x is irreducible if and only if f of x plus 1 is irreducible. So why is that true? If f of x factored, so would f of x plus 1. In our factorization, we could just take every instance of an x and replace it with an x plus 1. So you can see how this is going to generalize. Instead of x plus 1, you could put in x minus 1 or whatever you want. All right, so now this gives us another way to try to apply Eisenstein's criterion. Here's an example. Eisenstein's criterion does not apply directly to f of x equals x to the fourth plus 1. Why not? What we're looking for is a polynomial and some prime ideal in R so that all of the coefficients except the leading 1 for your monic polynomial are in that prime ideal, and the constant coefficient is not in the square of your prime ideal. But here the constant coefficient is 1. So you can't come up with any prime ideal P for which the constant coefficient is in that ideal. OK. But if you instead look at f of x plus 1, now you have to use the binomial theorem to see what that is. X plus 1 to the fourth plus 1, well, you just get x to the fourth plus 4 choose 1 times x cubed plus 4 choose 2 times x squared plus 4 choose 3 times x plus 1, and then plus 1 again, so you get a plus 2. Now, every coefficient is in the ideal 2z of z, and the constant coefficient is not in the square of that ideal 4z. So 2 divides every coefficient except the monic first one, except the leading one here, all the other coefficients, and 4 doesn't divide the constant coefficient. So now we can apply Eisenstein's criterion and see that this is irreducible because of the prime p equals 2. OK, so if this polynomial is irreducible, then f of x equals x to the fourth plus 1 is irreducible as well. Okay, one more application. Let's say that P is a prime. And define phi sub P of x to be x to the P minus 1 plus x to the P minus 2 plus x squared plus x to the 1 plus x to the 0. This is called the P Cycloatomic Polynomial. And this is going to come back and play an important role in 206C when we talk about the theory of fields. This is the subject of section 13.6. This is a topic I actually really like. When I was an undergraduate, I did an REU project about coefficients of cycloatomic polynomials. So I'll say much more about that later on. All right, so one thing we have to note is phi p of x is equal to x to the p minus 1 divided by x minus 1. How do you check that? Well, if you just take x minus 1 and multiply both sides by x minus 1, you can just expand the coefficients of x minus 1 times phi p of x and see that everything is going to cancel except an x to the p term and a minus 1 term. All right, so where does that leave us? Well, what is phi p of x plus 1? That is x plus 1 to the p minus 1 over x plus 1 minus 1, which is just x. We can see what the numerator is by applying the binomial theorem. And what we get is x to the p minus 1 plus p choose 1 times x to the p minus 2 plus p choose 2 times x to the p minus 3 plus p choose p minus 2 times x to the 1 plus p choose p minus 1. And this is p. OK? Every coefficient except this first, like 1 times x to the p minus 1. All these other coefficients, p choose 1, p choose 2, up to p choose p minus 1, these are all divisible by p. And the constant coefficient is p. So it's not divisible by p squared. So phi p of x plus 1 is irreducible by applying Eisenstein's criterion at p. But if this is irreducible, then phi p of x is irreducible as well. So this is a kind of neat trick that allows you to apply Eisenstein's criterion in situations where it's not obvious at first that it will be helpful.